Hi, good afternoon, everyone. My name is Shastri. I was here last month in the first session of the SLSA masterclasses. We did an introduction, so we'll go over a little bit of what we did last time. So this is the second session, and along with me is Zadi Kumar, an engineering manager at my company. Together, the two of us have been AppSec practitioners and application security folks for quite some time. What we want to do today is to give you a quick look at an attack on the software supply chain, and then talk about how you might want to protect it, how SLSA recommendations might protect it. Let's just take a quick look at what we did in the last session. In the last session, we started with real-life examples of software supply chain attacks. For example, we talked about the Barium supply chain hacking group. We talked about one or two of their hacks. We talked about the SolarWinds, one of the most famous recent hacks. Some folks consider even the Microsoft hack, the loss of their signing certificates, token signing certificates as part of the supply chain pieces. Maybe it is, maybe it is not. Microsoft doesn't give authentic information, though one of the reporters has given a very good investigative report. We talked about MoveIt. So these are some of the real life supply chain attacks that we talked about last time. Then we also talked about a visualization. We showed a visualization. We picked up graphics from the SLSA documentation itself. There is no need to reinvent the wheel. So we showed this document. We talked about the various stages, or if you want to even call them attack vectors on the software supply chain, A through H. And at each of the stages, what kind of attack can happen is something that has been annotated here. Then we introduced SLSA and SLSA v1.0 specifically. That is the latest, introduced in April this year. We talked about the concepts. We talked about the terms. This is one of the pictures from there. We talked about how the entire shaded green portion of it is a trusted platform, and then how the build process running on a trusted platform produces both the artifacts, that is the output of the build process, as well as the provenance. The provenance itself is required to be generated on the trusted platform. Then the provenance is attested, and consumers are expected to verify the provenance to make sure it is what they expect it to be, and then use it. So we talked about how SLSA requires the producers, that is the software publishers, if you want to call them, they need to adopt SLSA. The consumers need to adopt SLSA. They have a responsibility to verify the attestation. And the third one being the platform providers to provide certain basic SLSA enabling functions, make it easy to use SLSA, as GitHub does we showed in our demo last time, and provide a secure platform that can be trusted. So if all the three players are adopting SLSA recommendations, then this process is expected to take care of the supply chain security, except that this is not all. Okay, we don't want you to think that all there is to supply chain security is just provenance, signing the provenance, and verifying the provenance. There are a bit more pieces in the works. SLSA 4 is work in progress, but this is what we covered last time. Okay, we showed a SLSA 3 pipeline. So today, continuing, we'll pick it up from where we left off last time. We showed you just a general pipeline, and we showed how the provenance looked like, how the attested document looks like, attestation document looks like, and then we showed how the verification looks like. Okay, how a consumer might verify the provenance. Okay. Between last time and now, we have simulated many different attacks on a pipeline to see which ones of those are the best to show you in working, and then show you how adopting SLSA recommendations will help you secure your pipeline. But before we get to the demo, let's talk about a little bit about what we'll be showing today. We'll show the attack points at C and E. C, build from a modified source. E, compromised build process. Okay. There is some rationale to showing this. Okay. A and B are possible to be seen probably by SLSA 4 only. They are not covered until SLSA 3. Okay. Whether something on the producer side is compromised, that is an unauthorized change has happened, whether a compromised source repo has happened. D, on the other hand, is very easy to show, simple to show. I'll talk about it just in a bit. I also talked about it as an example that one of our own security folks did in a recent assignment for a Fortune 100 client. So we thought C and D are appropriate to show. Interestingly enough, while we did create both C and E attack scenarios, we are, as an organization, Clarinet Cybersecurity is an offensive security organization. So when we talk about hacking, we know exactly how to go and hack. We do that for our day job. However, the interesting thing that we realize is that the impact of both, once it is done, both of them appear to be the same from outside, from an external perspective. So rather than go into the details of what exactly we attacked and how exactly we attacked, this is not a hacking class. So what we want to do is to simply show you the compromise, show you the impact on the piece. So both C and D will be showing combined together, okay, and show the impact if we do it like a normal enterprise might in an insecure pipeline. So what Zadik will be showing you will be an insecure pipeline, okay, and then show that it can be compromised, and the compromised effect, okay, is not really detectable unless the attacker chooses to make it detectable. So since in this case, we want you to see that it has been compromised, so you will see it right on the home page that, yes, you've been pawned or something to that effect, okay? So, but then if the attacker doesn't want visible changes to be there, you really can't detect it. Then we'll talk about how adopting SLSA recommendations will stop this piece. Now, this piece of it, actually, we don't even need to show you really, because this attack itself will not produce the artifact. The build fails in a real attack scenario. So we don't need to really show that piece. All we need to do is, like, if you're not secure, how it will do, and then talk about how this piece works. Okay. How the build fails, what exactly happens is something that Zadik or I will talk to you when we come towards the end of the build. Let's just quickly see what happened in an A or B scenario and why. You will immediately realize why simply signing an artifact is not going to help. Okay, this screenshot I've taken from the mailing list of the PHP core team. Okay, now Nikita Popov is one of the committers there, one of the core team members, and in this mail he's talking about yesterday 2 malicious commits were pushed to the PHP SRC repo. Okay, so what happened? Somebody committed to malicious code to the PHP source repo, okay? And he said, from the names of Rasmus Lerdoff and myself. So somebody managed to act like, or hack their accounts, if you want to imagine, okay? Masqueraded as them and committed and authorized the commit to go through. So there is a two-step process. So somebody needs to commit and somebody needs to review and approve of it. So the commit was made as if Nikita had done it, and then the approval was done as if Rasmus had done it. Fortunately, they detected it within 1 day and then tried to investigate it. Okay. So the interesting part of it is in the second paragraph. Okay. While the investigation is still underway, we have decided that maintaining our own Git infrastructure is an unnecessary security risk. This is the interesting part. So this is where the platform security, one of the key elements of SLSA, comes in. What they realized is that securing their own Git infrastructure is not as simple as it looks, especially against this kind of attacks. So they went back into a hosted model where a service provider is assuring them of the security. Is that foolproof? No, it is not really foolproof. But since the service provider has a much larger security team and has much more resources to put in place, the chances are that they may do a better job so that the developers can focus on their part of it rather than try to maintain the infrastructure. That's why SLSA actually identifies clearly the producer, consumer, and the platform provider. Okay. So this is an interesting piece. So this is actually, for curiosity purpose, we can go and take a look at what actually happened. Okay. So you can see that this is from the, I took this from the GitHub, okay, of post their movement to GitHub. Okay. So what did it say? It says one changed file and Nikki C committed this. Okay. So it was done. Obviously, Nikita says that, no, I didn't do it. Somebody did it. And then they went and said, like, you can see the comment, remove this, sold to 0DM mid-2017. So whatever change was done, they were checking for a misspelled HTTP header. And if that header is present, they're going ahead and giving a remote code execution capability. The line here, line 37T, that shows here Zen eval string, okay, is the piece which says that whatever comes in, okay, actually gets executed. If it is null, of course, they give this output, but otherwise it evaluates whatever is the string that was passed in this header, HTTP user agent T. Notice the second T there. This is the malicious code that was put in. So it was given with Nikita's name, and in the next screen, you will see R. Lerdorf, Rasmus Lerdorf. Okay, it was signed off by him, says. So the same change was signed off. Okay, so this is how A and B can happen. Okay, D, on the other hand, is fairly simple. If you are not looking at dependencies in the right order, okay, for example, one of the recommendations that application security folks give is that make sure that the search path for your dependencies starts with your own repos, and make sure you have a trusted repo. You don't use a public repo, you clone a public repo of whatever open source pieces that you're looking at, and then use that public repo. Or if the public repo is hosted in a secure enough place, then use a specific version of it. In fact, don't even refer to it by tag or by version. Go for the SHA-256 hash of it. Refer to it by the hash, so that you're always sure that even if somehow the platform has been compromised in some way, what you're doing is that you're making sure that a commit with a particular SHA-256 hash is the one that you're picking up. Okay, so doing something like that will help you save against D, but otherwise, there will probably 99 or more than 99% of the enterprises don't necessarily follow all these pieces, especially the latest recommendation of referring to them by SHA-256 hashes are not done. So D becomes a little bit easier to attack. That is the dependency confusion attacks. Those of you who are in application security already know what the dependency confusion attacks are. So with that, I will stop and I will yield to Zaveek, who will show you a piece of sample software that he has developed and some infrastructure that he has stood up just to demonstrate this attack. Over to you, Zaveek. I'm stopping share. You can pick it up, please.
Thank you, Shastri. Hi everyone. Let me just share my screen. Hope you're able to see my screen. Okay, so basically this is an attack that we wanted to simulate so that we show how a build server compromise could lead to a larger impact. So for example, the setup that we have done over here is that we have a typical developer workflow where we have the source repository, and then basically we have set up a runner. This runner would build the artifact and then create the package, upload it onto a registry, and then the consumer will take that and then deploy onto the production server. So this is the basic setup. Over here, the build server has been compromised, and this is the demo that we'll be doing today. So this is the original code base, and I have opened up the actions sheet. So what I've used here is Gitia. It is an open source Git repository management system, and I have hosted it on an AWS server. So this is a custom domain that, this is the live site. So, and this is the final output. It's just a get API. So if I refresh it, you will see that this is the output right now. Okay. So what I would want to do is create a diversion wherein I redirect the traffic that goes out of the build server onto a different Git repo on a different server, and have the compromised code cloned from there onto the build server and then create the artifact. So let me just log into the server. Sorry. Okay, so I have logged in and I'm doing a very basic redirection of the traffic by changing some or inserting some entries into the etc hosts. And from there, once that is done, let me just rerun this pipeline. So basically what happens is we can do a commit here and then have it push, but just to make things easier, I'm going to rerun a previous pipeline that we have already done. So what happens here is it sets up the runner. So over here, since we're using Gitia actions, it is very similar to GitHub actions. It actually it builds on a Docker container, so that the in between builds and in between stages we get a clean build. So basically it downloads the Git the Docker containers, and then it runs the code that we have given it. So that is what is happening. So basically I am pushing this container onto the Docker hub. So over here the build has happened and the code has been brought in, the malicious code has been brought in, and it is going to get deployed onto this server. So we have two actions here. The deploy action would actually push it onto the server. So we'll just wait till it finishes. Yeah. So in this second stage, even though it's on the same server, since we have given it as a different build stage, it uses a completely different Docker container. So the installation of the dependencies, that is Docker, has to be done again, so that we log in and then we are able to pull the image. So now if I refresh this, the code has been changed. So now no matter how much or how many changes we bring into the code, for now, since we are redirecting traffic, all of this would actually be coming from a compromised site. So this is the compromised or the attacker Git, if you see attacker. And over here, I've actually changed the code. So as long as this redirection is happening, no matter what happens in the original code base, this is going to get built until I switch the code. Okay. So this is one of the things that we wanted to show. So basically, even though it has reasonable security, over here, it can be bypassed, and such very basic things can be done to actually redirect the traffic. Okay. I can't, sorry. Yeah. Okay. So what I wanted to show was, so basically, this is a pipeline that we have done on an on-prem Git server and on a self-hosted runner. This runner got compromised by the attacker and then redirected the traffic. And then we pushed the compromised artifact onto the production server. So in order to do the mitigation of something like this, there are certain guidelines that have been given by the SLSA on the SLSA. So basically what happens here, if you check on the SLSA 3, it is saying that it has to have a scripted build. It has to use a build platform. It has to have ephemeral environments, and it has to be isolated. So even though, since we're using Git actions and we are using a self-hosted runner, the ephemeral environment is only partially done, because even though we're using Docker containers, as you can see, even though it's happening like that, we can actually redirect the traffic. So we need to have an isolated environment where you cannot SSH into that build instance. So when it comes to GitHub Actions, they actually give something called GitHub runners. Same thing with GitLab. They have their own runners that we could provision. So enabling such kind of runners, even though there is a cost involved, it would actually allow you to be more secure and make sure that such compromises don't happen. Yeah. And one more thing that I want to talk was, like Shastri was saying, the code base that we use, that since a lot of the codes that are used in applications are actually from dependencies, like they say, only 20% of the code is written by developers, the rest of the 80% are dependencies. So whenever we actually point to a certain code base, for example, here we're using a reusable component, we are actually pinning it. So rather than say version 3.5.3, it would be just more secure to actually use the commit SHA. So if I gave it as version 3.5.3, it would be like trying to pin a moving target, because a tag can always be replaced. But the way in which Git has been created, the commit SHAs relatively don't move. So once it's created, it's set. So whenever you use such code from other repositories or other package registries, just make sure that you pin it to a certain version and it is reproducible. Make sure that it's not from a tagged version. Yeah, so so this is the full demo. That's it from my part. I just wanted to talk on these things. Yeah, and it's now back to Shastri.
Yeah.
So if any of you guys have any kind of questions, we'd be free to take them up right now.
Cool. So this was a very short session because, well, yeah, we showed you the attack, so we're not really explaining what, in fact, Zadik showed you how the traffic was redirected to rather quickly without explaining too much. What did we cover today? Let me just quickly summarize. We saw an attack on an insecure CI/CD pipeline. Okay, Zadik showed that he did not change the code. He ran the code. Originally, it showed a particular screen, but when he ran it for the second time after mimicking an attacker, okay, even though the entire build actions were actually referring to the exact same repo from a build instructions point of view, it actually reached out and obtained the code from a compromised repo. Okay. And as a result of it, some other artifact, a malicious artifact, got built. Okay. And in this case, not only was the build platform, self-hosted platform, the build software that was chosen also had a role to play in allowing it. Okay. It took us some time to be able to even get this far because not all software follow the same checks. For example, if you would try the same attack using GitLab, you will probably not get far at all, even if you're using a self-hosted piece. Okay, so different software have different weaknesses, and it makes sense to understand that you need to make sure that your platform has to be secure. And when in doubt, using a hosted platform is not a bad idea at all. A hosted service is not a bad idea at all. If your organization has adequate security, folks, by all means, go ahead for the self-hosted pieces. Check these out and use the right kind of a platform. Make sure you're securing it right. So we are, in today's session, we are talking about the SLSA recommendations. It's not only about the provenance that needs to be generated and the verification that needs to be done of the provenance. Okay, so maybe there are ways of actually detecting if there are issues in the process that can be detected by checking the provenance a bit more thoroughly. That is something that will require a significant amount of tooling and attack planning. So rather than make it too complicated, we did not do it now. Maybe in one of the future sessions, we might look at it. That's it for today. Thank you so much.
Thank you, Shastri. Thank you, Vivek. We don't have any questions. So yeah, we can close this.
Yeah, this was a rather short session. Thank you, Anvesha, for the opportunities, and thank you, Rupka.
Thank you very much.
Thank you. Bye.